Hello. Today we're going to be talking about U substitution. U sub is a relatively easy method of integration, but you might be wondering, when would I need to use this? Well, there are some integration problems that you cannot solve just by applying the power rule. Some have multiple functions. To use U sub, you have to have a function and its derivative within an integral, and then you must set that function to the variable u, or any other symbol that you wish to use, and put the integral in terms of u and du, creating a simplified integral that is solvable using the power rule. Let's go over a couple of examples. Here we have the integral from 1 to 2 of the function x plus 4 squared dx. We must ask ourselves, is this solvable using u sub? Well, we have the function x plus 4 and its derivative 1. So yes, u sub is an appropriate method to solve this function. So we will now set x plus 4 as u and its derivative 1 as du. Now we must rewrite this integral in terms of u. It is important to remember that we must also write the limits of integration in terms of u as well. So we will plug those limits of integration into x for our new equation u. We will now have the integral from 5 to 6 of u squared du. We can integrate this with power rule, which will get us u to the power of 3 over 3 from 5 to 6. Which is just 6 to the power of 3 over 3 minus 5 to the power of 3 over 3. Simplifying this with our calculators will get us 30.333. Let's try another problem. Here we have the integral from 3 to 4 of 3x times the square root of x squared minus 5 dx. Now, what do you think we should set as du? That's right, x squared minus 5, because that function's derivative is also in this integral. Now we can set du as 2x and begin simplifying. And again, we don't want to forget to also put our limits of integration in terms of u. So by plugging in 3 and 4 into x for our new equation u, we will find that the new limits of integration are 4 and 11. So rewritten, we have the integral from 4 to 11 of 3x times the square root of u. And as we can see, dx is equal to du over 2x, so that is what we will sub in for dx. The x's will cancel out, and we will be left with the coefficient of 3 over 2 times the integral from 4 to 11 of the square root of u, which we can now integrate using the power rule. And as you can see, these fractions are canceling out quite nicely, leaving us with 11 to the power of 3 over 2 minus 4 to the power of 3 over 2, which we can use our calculators to simplify to 28.483. I hope this has helped you understand the basics of u substitution. I will now pass this off to Alan to guide you in the realm of integration by parts.
Thank you, Caleb. Now we'll talk about the integration method called integration by parts. Aptly named because you divide the integrand into component parts, the basic scheme of an integration by parts problem is the integral of u times dv. And the result of such integral would be u times v minus the integral of du times v. You achieve du by taking the derivative of u, and you achieve v by taking the integral of dv. In order to properly identify which part of our integrand, u, we differentiate and which part, dv, we integrate, we have a nifty little key which gives us an order in which to choose u and dv. This is known as Lyeth, which stands for log, inverse trig, algebraic, trig, and exponential. Following Lyeth, our u would be the part of our integrand that appears first within our key, and dv would be the second part, which includes dx. Let us look at our first problem, the integral of ln of x dx. In order to choose the right component as u, we will first identify our two parts. We can see ln of x as 1, and while it might be tricky, dx is our second part. Based on Lyeth, ln of x would be categorized as a log and would therefore have to be our u, while dx would have to be our dv, since it includes dx. Following our basic scheme, we take the derivative of u and we take the integral of dv. Once we have these two components, we can get closer to our final answer. For our first half, we multiply u and v. For our second half, we subtract the integral of du times v. After doing this, we end up with x times ln of x minus the integral of x times 1 over x dx. After simplifying and solving this completely, we end up with our final answer being x times ln of x minus x plus our constant, c. Now let us look at our second problem, the integral of x cubed times e to the 2x dx. Our two components are x cubed and e to the 2x. Based on Lyeth, x cubed, and algebraic, comes before e to the 2x, an exponential. Therefore our u would be x cubed, and our dv would be e to the 2x. We can go ahead and find our du and our v. And after doing so, combine them into our answer based on the scheme. We end up getting 1/2 e to the 2x times x cubed minus the integral of 1/2 e to the 2x 3x squared dx. Our integral can be further simplified into 3/2 times the integral of e to the 2x times x squared dx. Now, you might have noticed, but this integral can't be integrated by normal means. It actually requires integration by parts to properly integrate. So now we must go through that entire process once more. We again have an integral that need integration by parts, so let me go through the process one more time. We finally got an integral that could be integrated normally. Now we must backtrack, plugging in the solutions to each of the previous integrals. This is our final solution to the integral of x cubed times e to the 2x. It is not pretty, but I would find it painful to simplify this, so you're gonna have to trust me. Now that we've gone through that whole process, I will show you a simpler way to integrate this kind of multiple stage integral, known as tabular method. In tabular method, you are still looking for u and dv. And you are still differentiating u and integrating dv. But you do not stop after doing it just once, you differentiate u until you come up with just 0. You then integrate dv, the same amount of times you differentiated u. After you have listed all your derivatives, you need to add alternating signs to them, starting with your u. Add a positive sign. Then add a negative sign to your first du. And then a positive to your second du, and so on until you reach 0. Then, you can match your list of derivatives to your list of antiderivatives. I will use arrows to show this. This signifies multiplication. Once you have matched all your non-zero derivatives, you can write them out as a regular mathematical expression, where you separate each match by the positive or negative sign that you gave each of them. Here is what we come up with after doing the tabular method. Our final answer from the tabular method clearly matches our final answer from the integration by parts method. If you cannot see that, then you must see an eye doctor. Thank you for your time.